Okay, guys, so let's get started. So basically what we have been doing the last two lectures is to, for 1 degree of freedom, basically we say is when there is one mass, okay, 1 degree of freedom, this example, we derive the equation of motion by defining that the motion is always divided into translation and rotation. So this is the equation defining the translation in general, and this is the equation defining the rotation, so the summation of moments. We wrote down some basic kinematics equations and we wrote down the procedure: dynamic by diagram, Newton's equations, additional equations from kinematics if needed, and solve. And we solve this problem over here. So for translation, we solve this problem over here for rotation. And again, we solve this one here for translation, but this time here, what happened is that we needed to take into consideration the static deflection, no? To look from, so we had that change of variable over here, the x equilibrium, and basically in all of them, we have the same type of equations. I don't know what that is. It's not showing up on my screen. Is that what you're seeing over here? Yeah, but the thing is that I don't see it here. It takes like 3 minutes. Oh, so it will go away by itself? Okay. You just need to request it online straight anywhere. Okay. So anyway, I'm kind of doing a review. So basically, that's what we did. Okay, here it's gone now. Okay. So today we're gonna kind of rederive the same equations of motions, but using what is known the energy methods. Okay. So let's go over here. So, and this looks easier, but personally I like a lot more the other procedure to find the equation of motion. So energy method, or energy methods to obtain equation of motion, EOM. Okay, so I'm going to do a derivation, but not in too much detail. Okay, but just to give you some idea. So I'm going to write over here the derivation. Is carried out in 1 dimensions for the sake of simplicity. But it is valid for 2D and 3D as well. Okay, so you might not remember this stuff, but the first one I'm sure you're gonna remember. Newton's second law is summation of forces equals to ma. This is Newton's second law. And maybe you study in calculus 3. I mean, you have studied that in calculus 3. Is that if the force is conservative, you can write it as the form of minus the gradient of a function phi, which is called, where phi here is, so this is the definition for a conservative force, where phi is known as a potential function. Okay, and from this potential function is where comes the name potential energy. Okay, but it should be calculus 3. Okay, where over here the del operator is equal to partial xi in 3D partial y j plus partial z k. Okay, so for 1D, it will just be this, okay? Okay, so just here to give you an example of the potential function. What is the potential function slash energy of a spring? What is the potential energy of a spring? Correct. So 1/2 kx squared. And what is the force of a spring? F equal kx, no? Okay. Or really, if you want, is in the opposite direction, minus kx, no? Or kx or minus kx. Okay. So let's see if this equation here is valid. So for 1D, we have F equal to minus dot of this one. So this should give you what? The spring force should be equal to what? Minus so minus partial x. What is the kinetic, the potential energy for the spring? Minus 1/2 kx squared, no? If you take this derivative, what do you get? Minus kx, which is the force of the spring, no? So this is valid. Okay? If you want, we can do one very quick. What is the potential energy due to gravity? mgh. So let's say instead of calling mgh, let's say it's mgx, no? So you take the derivative of mgx with respect to x, what do you get? mg. And what is mg? The force due to gravity. Okay, so you see this expression is valid, no? For conservative forces. Okay? All right, so let's put it here. So for 1D, let me just recall the two equations. Summation of forces equals to MA. And we had the force equal to minus a phi. So combining the two equations, what do I get? I get minus gradient of phi will be equal to MA. Okay, remember this is 1D, so this is equal to what? Okay, or we could say for 1D that this is equal to ddx, okay? To simplify. So for 1D, we will have what? Minus d phi dx equal to m second derivative of x dt squared, because we know that a equals dv dt, but it's also equal to the second derivative of x dt squared, no? Again, the derivation is not that important. Okay, so here comes now the trick of all this derivation that I will check in a minute. Okay, I will do the check. I can write this as minus d phi dx equal to M dt over t of, maybe this time will look familiar to you. So we have 1/2 M, and now I can say this one will be d dx dot of x dot square. What is x dot? Velocity or dx dt, no? Okay, so now basically what am I saying is that this term over here is equal to all this term over here. Okay, so let me go to the next page. I don't want to put too much on this page. So let's say check. All right, so let's say here check. So basically we're going to check that d dt of 1/2 d dx dot x dot square that this should be equal to this term over here, no? That's what I wrote over here. This term over here should be equal to all this term. Let's see if it's true. So let's see. What should be d dt 1/2 d dx dot x dot square. Okay, so if we do the inside first, what are you going to get on the inside? One half of what? 2 x dot, no? Yeah? Okay, so let me put the dot over here. So what's going to happen over here? These 2, is that the right one? This 2 is going to cancel this 2. And now, if I take the derivative in function to time, what am I going to get over here? X double dot, no? And what is x double dot? Is the same thing as d x square dt square. Okay, so therefore, what can I say? I can just go back to my previous equation, d phi dx equal to m d dt 1/2 d dx x dot square. Okay, so in this equation, m is constant. So if it's constant, that means that I can put it anywhere I want. So I can rewrite this as minus d phi dx equal to d dt of, okay, let me put this one, and this is also constant. I'm going to skip one step. So can I just rewrite this over here? D, well, here this is dx dot. Okay, don't forget to put the dot at the bottom. If it's constant, I can put those two constants anywhere I want. So it should be equal to what? 1/2 m x dot square. And what is x dot? is V, no? So really, what is 1/2 mv squared? What is really the physical meaning of this term? It's kind of kinetic energy, no? Okay, so okay, and I'm just going to put over here in most textbooks. I don't want to change the most textbook, comma, the potential energy is defined by the letter V. So basically what I'm trying to say in our problem, the field function that I defined at the beginning is going to be potential V, where V, okay, so we're going to have, so that we're going to have here minus dV dx equals d dt d dx dot 1/2 mx dot square dt. So in other words, where this will be here, kinetic energy. What is V? Is what we call the potential function, but this is the same as potential energy. Okay. Okay. Or I can write this as minus dV dx equals d dt of dk dx dot. Okay, so if you want, this is type A of energy equation. So this equation is absolutely valid. Okay, personally, is the one I use the most, but again, it's a matter about textbooks. Okay, and different problems. Instead, if you see something different, we're going to rewrite over here. Uh, three. In most textbooks, comma, the previous equation is defined as follows. Okay, so basically we have minus dv over dx equals d dt dk over dx dot. Okay, so basically I can write this as minus d dx. What I do is that I'm going to add one constant to each side because the derivative of that constant is 0. If you want, I can get into, I explain as soon as I write this line over here. Okay, so this is the original equation. V, what do we say? The potential energy of a spring is n 1/2 kx squared, no? It's in function of x, correct? So if you take the derivative in function of x, you're going to get minus kx or kx. All right? Now, the kinetic energy. Kinetic energy is what? 1/2 mv squared. So it's in function of v, not in function of x, no? So if you take the derivative in function of x, what are you going to get? 0, correct? So it doesn't matter if you add it to this term. Now, here's going to be the opposite. The kinetic energy is in function of what? X dot. So when you take the derivative with respect to x dot, you're going to get a value. The potential energy will be what? In function of x. So if you take the derivative in function of x dot, it will be 0, no? Okay, so basically you just add one constant on each side. I don't know why they presented this way, but at the end you can rewrite this, or you can write this as minus d L dx equal to d over dt d dx dot of L where L is the Lagrangian. Okay, so you want this is type B, and this equation is known as the Lagrangian equation. Okay, so you can use for me this form if you want, or this one, okay? The textbook showed this one a lot more. I think the other one is easier, but it doesn't matter. Okay. Okay, summary over here. So basically you can have two choices over here, but this is the important part over here is minus dv dx equal d. Maybe I should have done that before, but doesn't matter. dk dx dot. This one, in most cases, you're going to find out this form over here. You're going to find the form of d dx dot. This is d dt, sorry, d dt d dx dot of the kinetic energy plus dv dx equals 0. Or you're going to find the expression as minus d Lagrangian dx equal d dt dl dx dot, which is going to give you d dt of dl dx dot plus dl dx equal to 0. Okay, so what do we say? K is the kinetic energy. V is the potential energy. L is the Lagrangians. And here's important, X can be any variable. So basically, if we talk, I use X because we're talking about translation, but if it was rotation, X could be equal to what? X could be equal to theta, no? Okay, so it's not that it's X. This could be any variable, all right, that you need to use. X, Y, Z, theta, theta dot, okay? Whatever you need. Okay, and now I want to write one thing that we did the other day, but if you remember, I mean, this time, I will do it in the next page. All right, so let's look at kinetic energy just for a second. If something is moving in translation, what is the expression for the kinetic energy? K equal to what? 1/2 mv squared, which would be 1/2 m x dot squared, no? Now, if it's in rotation, what should be the kinetic energy? I is not theta. Theta dot, which would be omega squared, but yes, correct. So it would be 1/2 I theta dot squared, no? Okay. And now let's look at potential energies. And here I'm going to define something that we haven't done yet, but so let's say if you have a linear spring, what would be the potential energy? One half kx squared. Okay, so this will be again for, if we look at the type of what translation, no? Now you can have a spring at one point that generally you will do this type of figure. Okay, so this will be a rotational spring. So what do you think should be here the, so this one will be related to basically rotation. So what do you think should be then the potential energy? Also can be K, no? But it should be what? K. Here is X. Here should be what? Theta squared, no? Yeah. Correct? Okay. Okay, so let's do an example over here. Using energy methods, comma, determine the equation of motion for the below system. So let's do the below system before we decide anything. So basically, I'm just going to redo the same parameters that we had before. Okay, remember, this is what we did the other day, no? We had K, let's say no friction. This is M. And let's define here the motion from this point or here, this should be X. So if I didn't close the file, but I did close it. But basically, if we look at the lecture from the other day, what is the first case that we did? This one over here, no? Okay. What is the equation? So you see, this is the process. This figure, Newton's equations, additional kinematic equation, we combine, we found this equation over here. Okay? So we should find exactly the same by using the energy method. So let's see. Okay, so over here, which form of the energy method you want to use? Type B or type A? Type A, no? I like it a lot more personally, that's the truth, but it really shouldn't matter. But if you go to the textbook, you will see that they use a lot more type B, but you will rarely find type A. Okay? Okay, so let's say using the energy equation under the form minus dV dx equal to d dt dk dx dot. So maybe I can do it over here. Okay, I'm going to do it here because I want to have to redo the equation on the next page. So what should be the kinetic equation for that mass? One half mv squared, which should be what? One half m x dot squared, no? And what should be the potential energy? Let me start. Okay, potential equation or energy, doesn't matter. What is the potential energy over here? One half kx squared, no? So let me call this equation over here, whatever, A. So now if I say substituting into A, what do we get? So our equation is minus dV dx equal d dt dk dx theta. So if we substitute, what are we going to get? Minus d dx of what? 1 half kx squared equals d dt of d dx dot of 1 half m x dot squared. So the first term will give you what? you will get minus kx, no? Will be equal to what? D dt of what? One half times two m x dot, no? So these two will cancel. So what do we get? Minus kx will be equal to what? M x double dot. So this will give you mx double dot plus kx equal to 0. If you remember here, I can write this as what? X double dot plus k over mx equal to 0, or as x double dot plus omega n square x equal to 0, where omega n is the square root of k over m, which is what? The natural frequency. Okay, and obviously this equation is identical to this one, no? Okay, so now we're going to do the same thing for an object moving in rotation. So this is what we did before. Okay, that was a bit more complicated. Okay, you assume the small deformations, angles, blah, blah, blah. We need to do the parallax theorem, and we ended up with this equation, no? Okay, so let's see what we need to do now. All right, so let's do example 2. Or a new example. I don't know if I put numbers, example. So as before, using energy methods, comma, determine the equation of motion for the below system. So our below system is going to be the one we had before. So I'm going to plot here the undeformed bar. Okay, and now I'm going to do the deformed bar. There we go. Let me call this point over here O. So now the deformation will be in function of what variable? Instead of x will be theta. They say this will be the CG. This will be L over 2, L over 2. And this will have a mass M, okay? Okay, so I'm going to use, that's the stuff about this method and I don't like that much is let's call here that change in height H. Okay, and let's say that at this location, the value of the potential energy is 0. Okay, so maybe let's see if I can do it over here. Maybe not. Okay. I'm now redoing the figure, so we're gonna look at it from here. So for this figure over here, what should be the kinetic equation or kinetic energy? What type of motion is this bar having? Rotation. So what would be the kinetic energy? 1/2. Okay, this is important now. I, but when you define the I, you need to define about which point. So the I about which point? O omega squared, because if you put the CG, then it's not only rotation, also has translation. So probably this would be 1/2 I sub O, and what do we know? Omega is d theta dt, no? Okay, next, what would be the potential energy? What should be the potential energy? Okay. But we need to rewrite H in function of the variable that we know, which is theta, no? So what would be then H? What would it be? Okay, so you're almost right. Would be, if I factor by L over 2, would be is that distance over here, no? Which is L over 2, no? Minus the distance from here to here, no? Which is what? Is L over 2 cosine theta. Do you see this or not? Yeah, so basically this is our H over here. Maybe let me write it a little bit differently. This is H equal to mgl over is L over 2 minus L over 2 cosine theta, no? Okay, so next we're gonna say using the energy equation under the form. So before I write it down, this time instead of X, what do we have? Theta, no? So the equation becomes what? Minus dV divided by what? What are we going to over here? D theta, and over here we're going to have what? D theta dot, no? Is our variable. Okay? Okay, so substituting, we're going to get what? Minus dV d theta, oh, sorry, minus d d theta, sorry, of V. What do we have for V? We are mg L over 2, 1 minus cosine theta equals to d dt of d theta of what? Of 1/2 I sub naught theta dot squared. Okay, what is the first equation going to give us over here? If you do the derivative of mgl over 2 times 1, that should be 0, no? So what should be the derivative? What is the derivative of cosine theta? What should we have over here? Okay, but we have minus minus, so that becomes plus. Cosine is minus sine theta, so minus sine theta will be equal to what? D dt of what? I mean, same as before, but instead of x, we have theta. So at the end, what we're going to have, this is going to give us minus mg L over 2 sine theta equal to what? I sub naught theta double dot. Which is going to give us I sub naught theta double dot plus mg L over 2 sine theta equal to 0. Okay, remember I'm using exactly the same stuff as last time. So last time for this one, what did we use? Using these small deformations now. Okay, so let's say using small deformations, what do we know? Cosine theta is approximately what? 1, and sine theta is equal to theta. So that means that in our approximation, this is going to be approximately theta. So we're going to have that I sub naught theta double dot plus mg L over 2 theta equal to 0. Okay, this is correct 100%. And I'm not going to redo it again. I did it last time. What is I sub naught? Look at your notes. Is the moment of inertia about which point? About one of the ends of the bar, no? Okay. So if you remember last time, we did calculate it. We say, I don't know what it is. Yeah, we use the partial acceleration theorem. We move the moment of inertia from the middle of the bar, which is mL squared over 12, to this point using the parallel acceleration theorem. I sub naught is mL squared over 3, no? So this will be equal to mL squared over 3. But I mean, if you leave it this way, this is correct as well. It's just so that we have the same form as last time. So it will be equal to mL squared over 3 theta double dot plus mg L over 2 theta equal to 0. Or this will be equal to theta double dot, okay, plus mg L over 2 divided by mL squared over 3 theta equal to 0. This will be equal to theta double dot plus omega theta square theta equal to 0, where omega theta equal to the square root of what? So the m's cancel out, this L cancel out with this one. So we get what? G So 3G over 12. Okay, and this should be the same thing as we had before, unless I did something. 3G over 12, no? Okay, let me do one thing over here. Let's say over here, note. So let's see, previous example. Will be solved as follows. So basically, let me just redo the figure. We have class until 2, no? Okay. I teach all my classes one after each other, so I lose track. Okay, so basically this time what I'm trying to show you, that's why I'm doing this, is that what happened if instead of calculating the kinetic energy from point O, we calculate from point G. Okay, so let's say in this case, let's say so let's say kinetic energy. Okay, this time we say we take it from point G. So then what's going to happen? From point G, this is going to have translation plus rotation. Do you agree? Okay, so basically this equation will become now k is equal to 1/2 m x dot square plus 1/2 I sub g theta dot square. Okay, and then we'll have over here the potential energy. Will it be any change in the potential energy? Again, this will be H, there will be no change, no? Will be mg L over 2, 1 minus cosine theta, as before. So now, what is the problem? Is that this equation here is in function of theta, but this one over here is in function of theta and x, no? So we have a problem, no? No, no problem? Okay, so what do we need to do? You remember what was the procedure initially? Dynamic Billy diagram. Apply Newton's equations. 3 find additional equations, no? Additional equations from where? From kinematics. So for example, here, can we find the velocity? So here, x dot really is equal to what? At the velocity of point G, no? Yeah. Can we find the velocity of point G? The velocity of point G, we use the kinematic equation, will be equal to V sub naught plus omega cross R of G with respect to O. What is the velocity of point O? 0. So this is going to give us, try to keep everything in one page, IJK 0, 0, and omega, okay, and omega really is what? It's omega dot, no? I'm going to put here omega dot. And what is the position of maybe I should leave more space. Let me call this one. Can I just put this one R1, R2? Is that okay? Because what is R1, R2? What is the position? I mean, when is this place? What is the X position? What is the distance from here to here? From this point over here, from the CG at this location to this one over here, what is the X? What is the distance from this point to this point? L over 2 cosine theta. And then similarly, what will be R2? L2 sine theta. Should be, yeah, it should be positive, no? I mean, it doesn't matter really. So, I mean, we do all this stuff for a lot of work, which is not going to change too much. So if now we do the algebra for this, what we're going to get? Vg will be equal to what? So 0 times 0 minus R2 theta dot, no? That's what I'm saying. It makes a big difference what you do over here, no? To make it easier or more difficult. And then this one will be what? Minus R1 theta dot. See, one little change of changing where you take the moment of inertia involves a lot more work. Now, what is this? In other words, what does the bar means over here? What does the bar on top of the V means? It's a vector. Now, in this equation here, what is V? What is it? Scalar or magnitude, no? Correct? So how do we get the magnitude? So we're going to get Vg is equal to the magnitude of Vg vector. That should be equal to what? Minus R2 theta dot square plus R1 theta 1 square. And we'll take over here the square root, no? So this will give us what? Vg should be equal to what? So yeah, it should be basically R1, R2 is L over 2. I should have put L over 2, no? So Yeah, I mean, let me just put it this way because do I need to do one more? Yeah, I mean, let's do okay the algebra. Okay, I'm scared that you might not be able to see it. So this will give you what? L over 2 square sine square theta, theta dot square, plus L over 2 square cosine square theta, theta dot square. This will give you what? Vg equal to L over 2 square theta dot square, factor of cosine square theta plus sine square theta. We take the square root. What is cosine square plus sine square? 1. So at the end, what do we have? Vg will be equal to what? L over 2 theta dot, no? I mean, you see, normal algebra just by changing one little thing. Okay, and remember, maybe I forgot to put the most important part. Vg is equal to what? To x dot equal to L over 2 theta dot. So why did I do all this stuff? Because now, what can I do? Substitute into the kinetic energy. So what do we get? K will be equal, and maybe just rewrite it, 1/2 mx dot square plus 1/2 I sub g theta dot square. So this will give you what? 1/2 m. What is x dot? L over 2 theta dot square plus 1/2 I sub g theta dot square. Now you're going to see the beauty of this. This is going to give us what? 1/2 theta dot square factor of, then I write ig over here plus what? M L square over 2. Yes or no? Okay. What is this? Is this the same, exactly the same as this? Yeah. So really, this term over here is what? I sub. Oh, no? Okay. If not, make sure you reference that to the one to the previous class note. So where this will be sub off, because this is the parallel axis 7. So now, at the end, what this is that our previous assumption that we did, that we say what? K equal to what? 1/2 I sub O theta over dot square. As before, no? And then you can just follow exactly the same procedure. Okay, basically now we are exactly the same that as over here. Okay, so see that if you don't put the index, the value of the index over here, it might change a lot the problem, no? So not putting anything, I'm not even going to look at it. So don't think, oh, I'm going to be smart, I'm not going to put anything. If you don't put anything, I'm not even going to go look past that point, no? Because to write I without a point means nothing. It's like writing down the summation of moments. If you don't think about which point is useless, no? Okay, moment of inertia. If you don't think about which point, how is this called? Moment, no? Of inertia. If you use the moment equation, if you only find the points about which point you take the moments, that equation is useless. So basically, this is what you have now. I put over here. Continue, same. Okay, now just one more thing. I'm probably going to finish early. So today the problem we solve now is this one over here. And this is the ones that I like, okay? Don't think that I like the ones with the spring and stuff. So we have, let's see, this one here, this one here. This is theta. It doesn't matter what the stuff here, 0. Okay. So this is what we define as the continuous system. If I wanted to rewrite this one as a discrete system, how do you think it would look like? I mean, I'm just doing it because I defined it before. What type of motion is this going to have? So this, we could have a torsional spring, no? Resisting the torsion. Let's say with a bar of length L. And this will have, let's say at the end, I mean, let's just put it, if we needed to plot a mass, where here you will know what? M and, I mean, you will know basically I sub naught. M is not that important. And basically, if you were using this problem over here, okay, you want to put it, what would be then the kinetic energy? Sorry, the kinetic energy would be the one, I wanted to say the one, would be unchanged, no? Yeah? What would be the potential energy? 1/2 K theta squared, no? So maybe we don't have time today, but maybe if you want to think about it, what should be the value of K theta? Maybe we can do it from energy, no? Comparing those two equations. This equation here really should be equivalent to what? To this one over here, no? Yeah? Okay, so maybe we can find whatever, but we'll see what we do. Any question about what we did today? Is it getting complicated? Okay, 1 degree of freedom is okay. When we move to 2, will be a lot more complicated to divide the equation of motion. So we stop over here for today. Next time, I'll probably start 2 degree of freedom and we do a review from dynamics. So start working on the assignment. The first assignment should be very easy. When is it due? Thursday? Okay, this assignment is fine. The next assignment, you need to start early, okay?